Welcome back to the channel. Today, we're diving into a fascinating topic. How possible was the origin of man? Not in the form of man. Could centaurs, mermaids, gnomes, elves, trolls, or any other mythical creatures exist from a scientific perspective? We'll explore the latest scientific studies, ancient myths, and some mind-blowing possibilities that will make you question everything you know about evolution. So grab your popcorn, hit that subscribe button, and let's unravel the mysteries of human origins together. Don't forget to leave your thoughts in the comments and share your own migration stories. Let's get curious. Stay curious, and let's dive in. How possible was the origin of humans? Not in the form of humans. Is it possible for centaurs, mermaids, dwarves, elves, trolls, or someone like that from a scientific point of view? Although this topic seems fantastical, there is some relatively recent scientific news about it. For example, in 2020, two unrelated studies showed that in Central America, on the islands, broad-nosed monkeys have a tendency to come down to the ground. There are these broad-nosed monkeys called capuchins. Everyone saw them in the Pirates of the Caribbean movie, where a capuchin monkey with a coin was running around. These capuchins live in trees because they are afraid of predators like ocelots and jaguars. But on islands near the coast of Panama, where there are no such predators, capuchins descend to the ground much more actively and feel freer both day and night because no one eats them. In the jungles on the mainland where predators exist, they behave extremely cautiously, avoiding the ground and hiding at night, only coming out at certain times when predator attacks are least likely. Another similar but ancient news comes from Cuba, where there were fossil monkeys called parrillata. These monkeys were found on various Caribbean islands. Judging by their skeletons, these monkeys had a more terrestrial lifestyle than modern broad-nosed monkeys like howler monkeys. These island primates grew larger, up to about 20 kilograms, which is significant for South American monkeys. They became more terrestrial because there were no terrestrial predators. However, later on, the ancestors of modern Indians arrived on Cuba, Jamaica, Haiti, and other Caribbean islands, and this led to the extinction of the monkeys. To this day, it's still a question whether these monkeys survived until the arrival of Europeans because they disappeared around that time. So, evolution sometimes moves towards more human-like traits. But remember, evolution is a process, a survival statistic. It's not a woman with a club or a man with a rake sorting through what survives and what doesn't. And it's simply the mathematics of survival. So there's no universal law that dictates someone must evolve into humans or become like us. This actually opens up more possibilities because the history of life on Earth is incredibly rich, with many different forms emerging over 4 billion years, many of which had a decent shot at becoming intelligent. One of the key elements of our intelligence is our versatile hands. Biologically speaking, humanity is defined by 3.5 traits. Small canines, half a trait. Bipedalism, opposable thumb hands, and large brains. Our hands with opposable thumbs are crucial. While labor didn't create humans out of apes, it certainly finished the job, evolving Australopithecus into Homo. This co-evolved with our brains, but it could have happened differently. Based on mantises, crabs, or other creatures, we could imagine completely different paths. Arthropods, for example, have a wide variety of limbs and adaptations. My favorite, the acanthodes, could have multiple specialized limbs. One pair for cooking, another for writing, another for hearing. With more diverse functions, their brains might develop differently, solving new tasks we can't even imagine. Just like chimpanzees can't fathom flying to the moon, our own brain structures limit what we can conceive. But other species might evolve brain regions for tasks we can't dream of. In ancient history, back in the Paleozoic or even Cambrian periods, there were cephalopods, great candidates for developing intelligence. H.G. Wells' War of the Worlds imagines tentacled Martians, reflecting this possibility. Why go all the way to Mars when we have our own highly developed cephalopods in our seas? Modern octopuses, for example, have complex ganglia that function almost like our brains. They're incredibly intelligent. They can get angry, joke, hate play, and even engage in constructive activities. One of my favorite stories involves an octopus at an aquarium who was mistreated by a staff member. Whenever the staff member came near, the octopus would squirt water at them, remembering the mistreatment and retaliating. This behavior shows their impressive memory and emotions. Octopuses can also build simple structures, like stacking stones to create a shelter, and mimic other sea creatures like crabs, sea snakes, and fish by changing their color and texture. However, octopuses face several challenges. They lost their shells early on, and while some have internal shells, these aren't as supportive as a vertebrate skeleton. On land, an octopus would struggle to support itself. Though our ancestors managed to evolve from invertebrates to vertebrates with arms and legs, octopuses would need significant adaptation. Octopuses don't have parental teaching. Each octopus learns independently, but parents usually die before their offspring hatch, preventing knowledge transfer. Solving this would be crucial for any cephalopod evolution toward intelligence. Moreover, octopuses became perfectly adapted to their environment early on, leading to little evolutionary change since the Cambrian period. They're well suited to their marine habitat, which hasn't changed much. But who knows what the future holds? Other creatures like terrestrial arthropods, spiders, crabs, and insects also show promise. Insects like ants, termites, and bees exhibit remarkable collective intelligence, building complex structures and using sophisticated communication methods. However, insects face size limitations due to their exoskeletons. As they grow larger, their exoskeletons must thicken, becoming too heavy to support. This and the need to molt restrict their size and continuous growth. Besides, they have an open circulatory system. Their heart is just a simple tube that pumps hemolymph, a fluid equivalent to blood in insects, into the body cavity, where it bathes the organs directly. This system doesn't provide targeted delivery of oxygen and nutrients to specific tissues. For example, as I speak and think, my blood flows primarily to my brain, not so much to my left heel because it's not needed there right now. Insects, however, either activate everything or nothing at all because they have one body cavity where the heart just mixes everything. Insects also have a tracheal respiratory system, tubes that permeate their entire bodies, allowing gases to diffuse directly. These tubes even penetrate the brain, meaning air literally flows through their heads. However, as insects grow larger, diffusion becomes insufficient to transport oxygen to distant body parts. That's why fossil insects like Meganeura, a giant dragonfly, could reach about 30 centimeters in length, and modern stick insects can grow to similar lengths, but not beyond. They remain thin and long because they can't increase their body volume significantly, limiting their brain size and intelligence. These challenges are theoretically solvable, as our ancestors faced similar issues. Insects have just found their niche and stayed there. If you didn't know, we live on a planet dominated by insects. There are more ants in a single field than humans on Earth. Insects have evolved in their own remarkable ways, with various forms and social structures like ants, termites, and bees. Their evolutionary limitations from their past have held them back, but there are other candidates for advanced evolution. For example, fish. At some point, fish ventured onto land, becoming tetrapods and eventually evolving into mammals and humans. Other fish, like lungfish, also moved onto land but adapted too well to their semi-aquatic lifestyle. Lungfish can bury themselves in mud, forming a mucus cocoon and surviving for up to 4 years until rain revives them. This excellent adaptation to drying conditions kept them from evolving further onto land. From the Paleozoic era, spanning hundreds of millions of years, creatures like lobe-finned fish and coelacanth, such as the Latimeria found near the Comoros and Sulawesi, showcased remarkable evolutionary traits. These lobe-finned fish, similar to our ancestors, lived near the shores and eventually ventured onto land. However, coelacanth became deep-sea dwellers, walking on the ocean floor with limb-like fins, remaining largely unchanged for about 400 million years. A fascinating example is the acanthodians, small fish with multiple pairs of fins. Our ancestors had pectoral fins, now our arms, and pelvic fins, now our legs, while acanthodians had up to 7 pairs of fins. These extra fins could have led to diverse evolutionary paths, potentially producing centaur-like creatures with multiple pairs of limbs. They could have evolved more quickly by skipping stages like climbing trees and developing bipedalism. With horizontal spines, these creatures could have expanded their brains faster, avoiding the balance issues and spinal problems humans face. In the Paleozoic era, they could have exploited new environments, preying on emerging insects and developing complex behaviors. By the end of the Paleozoic, hypothetical intelligent beings might have emerged long before humans. Imagine these creatures with horizontal bodies, free forelimbs, and a vast array of brain functions. They could have developed advanced skills, utilizing their multiple limbs for various tasks. While this is purely hypothetical, it demonstrates the limitless possibilities evolution can offer. The acanthodians faced a major challenge. They lived in the well-lit upper layers of the ocean, not near shores or rivers. They were perfectly adapted to their three-dimensional aquatic world, streamlined and fast, with no need to venture onto land. As a result, some evolved into bony fish while others went extinct. When our ancestors did emerge onto land, they explored various adaptations. Early tetrapods like Acanthostiga, Ichthyostiga, and Chictalic exhibited different numbers of digits. While our 5-digit configuration prevailed, there were 6- and 7-digit versions, like the Tullerpetten with its 6 fingers and toes. Visiting the Paleontological Museum in Moscow, you can see these unique limb structures. Our ancestors ultimately retained the 5-digit form, although horses evolved to 1 digit and ostriches to 2, making them more specialized than us. Evolution could have favored other configurations, like multiple limbs resembling tentacles or lateral branches. As amphibians evolved into reptiles and eventually synapsids, various paths were explored. For example, therapsids like therocephalians and cynodonts were similar. Cynodonts, our direct ancestors, developed features like secondary palates, allowing for advanced olfaction and efficient eating. This adaptation separated the nasal and oral cavities, enhancing their sense of smell without hindering eating. Therapsids, covered in fur and potentially giving birth to live young, were precursors to mammals. Despite these fascinating divergences, cynodonts emerged victorious, leading to the mammals we know today. Therocephalians, on the other hand, had different skull structures and never developed a proper secondary palate, limiting their diet to small prey. This restricted their growth and prevented them from becoming large predators or herbivores. Their olfactory senses remained underdeveloped compared to cynodonts, our ancestors, whose forebrain evolution was heavily influenced by advanced olfaction. As cynodonts evolved, they developed a secondary palate, separating the nasal and oral cavities. This allowed for a powerful sense of smell and efficient feeding, crucial for survival. These adaptations led to the dominance of mammals, while therocephalians faded away by the Triassic period. Numerous mammalian lines emerged, each with unique adaptations. Multituberculates, for instance, developed highly specialized teeth, but ultimately lost out to more versatile rodents and primates. Marsupials, too, explored various niches, but faced limitations due to their reproductive system, where they gave birth to underdeveloped embryos. Among later primates, Gigantopithecus is one of my favorites. These massive apes had the potential for significant brain development and could have become a peaceful, large-brained species. Imagine gentle giants like Buddhist sages philosophizing in bamboo forests. However, they face competition from more adaptable Homo species migrating from Africa. Climate changes and evolving ecosystems further challenge Gigantopithecus, leading to their extinction. Similarly, lemurs in Madagascar, an isolated ecosystem, evolved unique adaptations but remained limited by the lack of significant predators compared to mainland Africa. On isolated islands or closed environments, even more primitive creatures like reptiles or dinosaurs could have evolved into intelligent beings. If dinosaurs had been isolated on a large island or a place like Australia and hadn't gone extinct, they might have developed intelligence. However, reptiles lack a neocortex in their brains. Even though they might develop one, their strong jaws and horizontal body pose challenges. Dinosaurs, and birds for that matter, have vertical legs but horizontal bodies. A large head would be cumbersome, making it difficult to balance. They must choose between large jaws for predation or large brains for intelligence. Both aren't feasible. The laying of eggs also limits them, as hatchlings are born at a fixed size and can't be nurtured for long periods. Although some reptiles and amphibians show rudimentary care for their young, it's not enough for advanced development. Birds could have evolved intelligence, given some species like New Caledonian crows and kea parrots show remarkable cognitive abilities. However, flying necessitates lightness, and a large brain would be detrimental. Birds' brains are good in their own way, with well-developed subcortical nuclei, but their behavior is largely instinctual and pre-programmed. Their rapid development from hatchling to flight readiness leaves little time for extended learning. Double respiration in birds complicates live birth, limiting them to egg-laying and reducing the potential for extended parental care. With quick maturity, there's less opportunity for complex learning. Returning to primates, other species like Homo naledi and Neanderthals could have become modern-day gnomes. Living in caves or underground might lead to reduced resources, smaller brains, simplified structures, and cultural loss over time. Subterranean existence leads to sensory reduction and a lack of large predators, resulting in simplified lifestyles. While cave creatures like Proteus salamanders can live long, their inactive and sensory-deprived lives don't favor advanced intelligence. Theoretically, some primates or other creatures could return to the water and become some kind of ichthyanders, water-human hybrids. However, there are several limitations. The human brain is highly energy-intensive, requiring a significant amount of calories and oxygen. If we converted the oxygen requirements of a human brain, weighing about 1.5 kilograms, into fish gills, the gills would need to be the size of a stadium. Although more accurate calculations show they wouldn't be quite that large, the gills would still be impractically big. Take beavers, otters, seals, whales, and dolphins, for example. They have some amazing adaptations. Beavers build dams and slap their tails on water. Otters are lively and resilient. Seals are playful, and dolphins are intelligent. However, as these animals adapt to aquatic life, their limbs transform into flippers, and in dolphins, legs disappear entirely while their arms become fins. This limits their ability to perform complex tasks. Our intelligence is tied to our ability to manipulate objects with our hands, which dolphins and other marine mammals cannot do. Dolphins have demonstrated the use of tools, such as grabbing sponges or coral pieces to stir up sediment and create a murky ring to trap fish. While they show some signs of intelligence and even have what appears to be a form of language, their intellectual capacity remains limited. Their primary task is to outsmart fish, which does not require advanced cognitive abilities. Additionally, dolphins' dental systems have simplified with pointed teeth or, in the case of large whales, baleen. This limits their culinary diversity. Our varied diet has driven much of our progress. So, while ichthyosaurs could theoretically evolve, it would likely require genetic engineering rather than natural evolution. The challenges related to their skeletal structure, limbs, breathing, and heart function would need to be addressed. So, evolution has indeed created many alternative developmental paths, from invertebrates to the first fish, amphibians, reptiles, mammals, and among mammals, various primates and other species. However, each path faced limitations. The unique combination of circumstances that led to humans was the only one that fully realized. This doesn't mean other possibilities can't exist, but their likelihood is very low. Just like there is only one species of aardvark, one species of giraffe, and one species of ii, there is only one species of Homo sapiens right now. The probability of another intelligent species emerging is very slim. There were other alternatives, like our ancestors becoming intelligent due to tree-dwelling habits. They could have specialized in gliding or flight, like Colugo with gliding flight or bats with true flight. However, these adaptations imposed significant constraints. Flying mammals, even warm-blooded and viviparous like bats, can't give birth to large-brained, heavy offspring due to flight limitations. Bats live long, around 20 years, and have social structures, like vampire bats sharing blood. But they can't develop large brains because they need to quickly learn to fly and harden their bones, making large heads impractical. Theoretically, bats could become intelligent if they reverted to a terrestrial lifestyle. Birds like penguins and ostriches adapted to land under specific conditions, but they don't need to develop intelligence. In environments like Antarctica, survival and competition with predators are more critical than intelligence. On islands, birds like the dodo or flightless cormorants thrived without the need for high intelligence. Ostriches in the African savanna, where our ancestors evolved, don't need to be intelligent. They are large and fast, capable of defending themselves with powerful kicks. Bats never returned to a terrestrial lifestyle, possibly due to their specialization and unique limb structures. While it's theoretically possible, it hasn't happened yet. Evolution provides endless fascinating possibilities and pathways, shaped by various constraints and circumstances. There are indeed other intelligent creatures like elephants. Elephants are known for their intelligence, memory, and social structures. They can perform tricks, paint pictures, and use their trunks as tools. Elephants have leaders, usually the oldest and largest female, and they can migrate long distances and dig for minerals to supplement their diet. They nurture their young for a long time, and their brains can weigh up to 9 kilograms, averaging around 4 kilograms, significantly more than the average human brain. However, despite their intelligence and tool-using abilities, elephants face few threats from predators. Large size and social grouping provide safety, reducing the need for further cognitive evolution. Historically, predators like saber-toothed cats posed a threat, but today, only rarely do lions target elephants, usually in desperate situations. Elephants have evolved significantly over 40 million years, adapting to various environments and growing larger brains. Yet their herbivorous diet simplifies their challenges. They mainly need to find food and water. Unless their size decreases, making them more vulnerable, or they face new challenges requiring enhanced intelligence, Their evolutionary path toward greater cognitive complexity remains uncertain. Other creatures in similar ecological niches could have evolved intelligence, particularly among predators. Carnivores have complex social interactions and hunting strategies, which might drive further cognitive development. Humans evolved from tree-dwelling, omnivorous, social ancestors with grasping limbs. When considering predators, different groups have their limitations. For instance, felines, even social ones like lions, are highly specialized hunters with no need to develop further. They hunt prey like zebras or antelopes, and their evolutionary path doesn't require advanced social behaviors or intelligence. Omnivorous but non-social animals like bears are ecological analogs to humans. Bears eat a diverse diet and live in similar environments but lack social structures. Their interactions are minimal, usually limited to gathering at salmon runs. While bears are intelligent compared to other forest creatures, their solitary nature limits further cognitive development. Another intelligent creature, although not a predator, is the pig. Pigs are also omnivorous and share some anatomical similarities with humans. They even hunt small deer and have versatile diets. However, pigs have specialized limbs, hooves, that restrict their ability to manipulate objects, thus limiting the development of advanced intelligence. Another intriguing possibility lies with canids, particularly wolves. While dogs are intelligent, wolves are even smarter. Wolves are ecological analogs to humans. They eat a varied diet, can live almost anywhere, and are highly social. They raise their young, teach them skills, and have been observed using tools to a certain extent. One fascinating story involves a group of wolves in the Caucasus that drove elk onto a sharp stake, using it as a hunting aid for generations. When the stake rotted away, the wolves were left confused, and the group eventually died out. Despite their intelligence, wolves face limitations. They are strictly terrestrial and haven't evolved the versatile hands needed for tool use. Their paws, while agile, aren't designed for grasping and manipulating objects. This limits their potential for developing advanced technology or complex problem-solving. Dogs, although intelligent, often rely on humans for problem-solving and lack the independence of wolves. The smartest dogs, like Lycus, which are adapted to their environment and solve problems independently, show remarkable autonomy. Raccoons are another potential candidate. They are partially arboreal, omnivorous, social, and have versatile hands. They live in diverse environments, from forests to urban areas. However, raccoons have also remained largely unchanged for millions of years. Their highly developed sense of smell and claws for climbing and grasping might have limited their evolution towards more advanced intelligence. That's a great point. Our ancestors also went through significant changes. In the Paleocene, they didn't have grasping hands either, but as they specialized as tree dwellers, they lost some of their sense of smell and developed better vision and hearing, eventually leading to speech. Raccoons, however, are climbers, not jumpers. They have short, stocky legs and lack the specialized joint for jumping like our ancestors did. Jumping from branch to branch helped our ancestors develop coordination and quick thinking. This also provided safety from predators. Raccoons climb trees but don't jump far distances, which makes them slower and less agile compared to monkeys. Raccoons rely heavily on their sense of smell. Their large noses and reliance on olfactory cues might limit their cognitive development. While it's theoretically possible for an intelligent species to evolve with a strong sense of smell, communication through gestures and sounds is much more efficient and allows for more complex information exchange. Imagine trying to convey complex concepts like calculus through sense. Drawing or speaking about it is much more practical. Raccoons' dependence on smell over vision and hearing, along with their clawed, climbing fingers, seems to have hindered their evolutionary path towards higher intelligence. Indeed, primates like capuchins, chimpanzees, or even gibbons are our closest relatives and the most likely candidates for evolving higher intelligence. However, as we've seen, their evolution often takes different directions. Chimpanzees, for example, develop knuckle walking, making it difficult for their hands to evolve into tools like ours. Their teeth have also become larger over time. Bonobos, or pygmy chimpanzees, are known to be more peaceful, but our ancestors were even more sociable and cooperative. The major challenge for any potential candidate today is the presence of humans. We are the ultimate competitors, occupying all ecological niches and dominating the planet. Intelligence requires a lot of energy and space, which humans have monopolized. Science fiction often imagines alternative intelligent beings, but they usually end up being variations of humans, perhaps with pointy ears or some animalistic features. Yet, imagining intelligent raccoons, advanced cephalopods, or even centaur-like beings derived from fish is far more intriguing and possible in an evolutionary context. Who knows what the future holds? Perhaps with advancements in genetic engineering, we might see some of these ideas come to life. In evolution, there's an interesting, if somewhat ironic, rule that the most advanced, remarkable progress often arises from the most primitive and insignificant beginnings. Highly specialized and advanced creatures tend to reach a peak where they no longer need to evolve further. They are perfectly adapted to their environment, with no need for drastic changes. Humans are unique in that our ancestors were relatively average and nondescript, constantly facing challenges that forced them to evolve. For example, take the platypus. It's a fascinating creature with a duck bill, laying eggs, possessing electroreception, and having a venomous spur on its leg. Despite these unique traits, it's highly specialized and unlikely to evolve further into something significantly different. Similarly, humans have lost certain features over time, such as tails, vibrissae, whiskers, and many teeth, reducing our potential for new evolutionary adaptations. In contrast, burrowing creatures like shrews, which have remained relatively unchanged for millions of years, demonstrate that significant evolution can still occur from these humble beginnings. Nevertheless, our next evolutionary stage might not be far off. This was the Curiosity Dude urging you to subscribe to the channel. And like the video, if you have insights into alternative intelligent beings or knowledge about reptilians and other humanoids. Share your thoughts and research, engage with friends and family, and inspire children to dream big and write imaginative stories. Together, let's push the boundaries of our understanding and creativity toward a bright future. Stay curious and keep exploring.